So to start, machine learning has a lot of buzz around it, as I'm sure many of you know. In the room, can you tell me what are some of the big use cases that you've heard on machine learning?
Autonomous vehicles.
Autonomous vehicles? What else?
Spam filters.
Spam filters, that's a big one. Anything else?
Autocorrect.
Autocorrect, yeah, on your phone.
Facial recognition.
What was that?
Facial recognition.
Facial recognition, yeah. Yeah, there's tons of stuff. I mean, it's in the news all the time. Whether it's handwriting recognition, autonomous vehicles, understanding your voice, right? When you speak to Siri, there's a machine learning algorithm converting your speech into voice. Machine learning is kind of pervasive in our society today, but it can be hard to understand what exactly is going on behind the scenes. And so that's what I want to give you a little bit of an introduction to today. To start with, machine learning is within the discipline of what we would call predictive analytics, to help kind of define predictive from descriptive. A lot of what we do in descriptive analytics is we deal with data that is historical and known, right? It's real data, it's a fact, it can't really be disputed. So you deal with raw data points, you summarize data, you do calculations on existing fields, you put together KPIs, you visualize those, and you hope to get some sort of insight out of that. When we get into the predictive realm, what we're doing is we're actually generating new points of data that have some uncertainty to them, because they either represent something that might happen in the future, or a decision that requires some sort of intuition or some sort of uncertainty. And we can take those values and we can do sort of the traditional analytics BI things with them, right? We can include them in dashboards and we can present them to stakeholders. But what it really comes down to with predictive is we're generating new data that has uncertainty built into it. In the past, predictive analytics was a highly manual activity that required a lot of high-paid and highly educated individuals to take a lot of their time to come up with a single model. Predictive analytics works often by assigning weights to data inputs to put together a data output that you hope represents some future outcome, right? And traditionally, it would take human experts weeks or months to consider just a handful of variables, 5 to 10 variables per model. They would get a model, they would put it into production, it would be making predictions. Meanwhile, it's making predictions and the environment is changing around it. So the performance of the model, the goodness of its predictions is degrading over time. And they don't get back to reviewing that model for a year, sometimes 2 years. And in the meantime, your model is just not doing as well. Machine learning kind of changes the way that we build predictive models. In that, number one, it allows us to consider a much larger amount of data. And number two, it can actually be built to self-adapt over time, so that as the environment is shifting, your model's weights are shifting too, to continue to reflect the new reality. So machine learning makes predictive analytics cheaper, and it makes it more effective, which is a pretty good combination. There are generally two flavors of machine learning. The first is called supervised learning. In supervised learning, what we have is we have a right answer that we can give the computer. So that might be because we have some history, some historical data that we can look back on and say, in the past when this was done, this was the correct outcome. And then the computer can go and learn the patterns that led to that outcome and make predictions in the future. Or the second might be hoping to replicate human decision making, right? So a big example of this is the self-driving car, right? So the car is taking video all around it, and it gets an idea of what the road looks like. And then it might say, okay, the last time the road looked like this, my human driver turned the wheel slightly to the left. So the next time the road looks like this, I'm going to turn the wheel slightly to the left, and I'm going to emulate the human. The human has labeled this road pattern for me as a slight left turn. And so that's a supervised learning situation. The other possibility, and we're going to spend less time on this because it's not as readily applicable, or people don't typically think of it right away in terms of use cases. There are great use cases for this, but people aren't going to probably ask for them so much as we have to suggest them. But for exploratory data analysis, unsupervised learning, finding patterns in data to help you group the data together or to help you understand the variance in the data or the relationships between the variables in your data. In these situations, you don't necessarily have right answers. All you're working with is the relationships of the data. So to kind of drive this home, we'll do a few quiz questions. Is this an example of supervised or unsupervised learning? Predicting our profits for next quarter. Supervised. Good. All right. Identify the number that has been written on a check that you want to deposit. I'm hearing a couple unsupervised. It's supervised because there is a correct answer, right? So we draw the number and then we label it, that's a 6, right? And then we have to tell the computer that's a 6. Group our customers into segments.
Unsupervised.
This one's unsupervised. Predict a user's rating for a product. Supervised. The user can go back and label it. You might not get a label, but that's what you're training on is labeled information. Find the most important variables in a data set. Unsupervised, yep. Identify credit card transactions that are out of the ordinary. Supervised. This one's a trick question. This one's unsupervised. If it was identify fraud, where it's labeled as fraud or not fraud, that would be supervised. But if you're just comparing transactions to one another and trying to figure out what's out of the ordinary, that's an unsupervised problem. So the machine learning process, regardless of whether you're doing supervised or unsupervised learning, can essentially be boiled down to 4 steps. There are tons of algorithms out there. They all essentially do these 4 things. You create a hypothesis. Typically that hypothesis is either random or you start with whatever people have been doing in the past. So however you've historically predicted your sales, you start with that as your hypothesis. And then you evaluate the hypothesis. So you have to tell the computer how to measure how good or bad the hypothesis is. You make an adjustment to the hypothesis, and then you repeat that rapidly until you get to a hypothesis that's either good enough where you're satisfied or until there's not enough information in the data to improve anymore. And to illustrate this process, I'm going to take you through something called gradient descent. We're going to use a sample data set that I just got out online. This data set we're going to see several times today. Actually, when we get into the tools, we're going to show how Python handles this data set to get a predictive model. We're going to show you how R handles the same data set, and then Azure Machine Learning. So you'll see it a few different times in a few different ways, so you can see sort of the differences in how they implement the same thing. But for now, what I've got here is just it's a data set of almost 400 cars, all between 1970 and 1982. This is the bottom of our list, so you see these are the later cars. We've got miles per gallon, cylinders, displacement, horsepower, weight, acceleration. And for the purposes of this first demonstration, to kind of help you get the intuition behind gradient descent, we're gonna limit our variable set just to miles per gallon, weight, and year. Okay, and what we're gonna try and do here is we're gonna try and create a model that predicts a car's miles per gallon, given its weight and what year it was manufactured. Okay, we're just going to limit it to that. And so we're going to start by creating a hypothesis. And our hypothesis is that if we multiply the weight times some number, and we multiply the year times some number, and we add those two things together, we'll get a prediction for our miles per gallon. And we're going to start with our multiplying the weight times negative 0.02. We're going to multiply the year times negative 2, and that's going to get us our prediction. So now we're going to look at our data set here with those predictions. We've taken our weight and multiplied it times minus 0.02 and our year times minus 2, and that gives us these predictions, which are pretty clearly terrible. They're all negative, which most cars do not have negative miles per gallon. So clearly we can do better. But first we have to figure out just how bad these are. We have to give the computer a way to objectively state how good or bad they are. And what we're going to use for that is called mean absolute error. So we're going to take the difference between each of these, between each of our predictions in each of our NPGs, our actual values. We're going to take that difference, take the absolute value, and then find the average of all of those. So our mean absolute error is about 250. So on average, we're off by 250 miles per gallon. That's our starting point. Now we're going to adjust the hypothesis. And for this adjustment, we're just going to kind of take a random guess. Let's add 0.06 to our old multiplier for weight and add 1.9 to our old multiplier for the year. And update our predictions. And now we've got this set of predictions here in the far right column. So we're doing better. We're positive at least. Still pretty far off. 95 isn't very close to 27 and so on. So now we're going to evaluate round 2. So our last MAE was 250. Now we're at 73. Okay, so that's better. But there's got to be a better way to do this, right? Obviously. Thankfully, since we only have 2 variables in this current analysis, we can actually plot everything and pretty easily visualize all of the reasonable sets of answers, right? What all of our weight multipliers and year multipliers could be. And if we do that, we get a curve that looks like this, okay? So you can see on the vertical axis, we've got our mean absolute error, and if we were to choose this combination of year multiplier and weight multiplier, we would get a MAE of 309, and if we move down here, we'd be at 45. And so our goal is to minimize the minimum absolute error, so where we want to get is to the bottom of this curve, right? And you can see that, well, obviously there's sort of a crease this way, so we want to be somewhere in this valley. If you look here, you can kind of tell that it's got a little bit of a bow to it, so we want to get to that minimum point. Right, so we can look at this and say, all right, well, we want to be, well, somewhere around here where it's in like the single digits, ideally. There, that looks like a pretty good way to find our prediction. So we should just set it there, right, at 0.0 something and, well, whatever they were at, right. We can also take this and we can look at how our previous 2 predictions, where they were on this curve. So this was our first prediction, it was up here at 250. If we add our second prediction, it's right there. So our second prediction, we actually overshot the minimum, right? We're on the other side of the valley, and we're on the other side of our minimum point. So we actually overshot. So if we kept updating it in the same way by continuing to add 1.6 and 0.8 or whatever it is we added, right, we would actually be getting further away and getting worse. So what can we do instead to get to the bottom of the valley, right? I mean, in this case, we've got 2 variables. It's easy to kind of look at it and say, all right, well, that's our best answer right there, right? But what do you do when you've got 3 dimensions, right? And then you got 4, you've got 5. We can't visualize that anymore. But the computer can handle that because the computer can do linear algebra. So what we can do is we can take a sort of a similar approach. We're gonna continue in this sort of 3-dimensional space for now because it's easy to visualize, but the computer can do this in much greater dimensions. But what we're gonna do is we're gonna start from our first guess, and instead of just taking a random guess or instead of just looking directly, at the minimum, we're gonna tell the computer to start there and just take a step downhill. Okay? We're just gonna take 1 step downhill, and then we're gonna see where we are, and we're gonna do it again and again and again until we can't get any better. All right? And so what I've done here is I've created a formula, a function that's just gonna take that process and do it iteratively for a number of steps that we tell it to do. The key thing here really is the math behind the how do we know what downhill is. All you've got to do is think back to your high school calculus. We're just finding a derivative, right? We're finding the slope. And once we know what the slope is, we know we can take a step downhill because we just say, okay, which direction is negative in the slope? That's where we want to go. So that's the most complex math we have to do here is just find the derivatives. We're going to tell it to take 100 steps, and they're going to be very small steps. And what happens? All right, so we started at 250. After 1 step, we're at 204, and so on. And it looks like we get stuck at 50. Yep, we got stuck at 50. Okay. It's still going down, but it's going down much slower. So these are our new weights that it found, right, where our mean absolute error is 50. These are our new predictions. They're negative again, so that's not good. So something happened here, right? What happened? Well, let's visualize the steps that we took. All right, they go way off to the side. Anybody have an idea why they go way off to the side without reading ahead?
Because there's two slopes.
Two slopes.
You have one down the normal face and then the other direction that's going down as well. So it's not going straight down, it's going at an angle.
Any other ideas? Take a look at the scale of our two axes there along the bottom. This one covers about 30. This one covers about 0.1, right? So a tiny step is going to look very small along this axis, and it's going to look pretty big along this axis, right? And so we've come up against a big problem in machine learning that we see a lot, and there's a solution to that. We call it normalization. And really what we're doing here is we're playing with the variables, right? So instead of using the 2-digit year, we could use the 4-digit year, and that might get our variables closer to being on the same scale. Or instead of using the weight in pounds, we could use the weight in tons. That might get it onto the same scale. What we're going to do is we're going to apply a more general technique, which is called normalization, where we're actually going to, this is called a min-max normalization. For each car's weight, we're going to take that minus the minimum weight, and we're going to divide that by the range of the weight. Okay, so that way we sort of get a percentage between the minimum and the maximum. So if all of the weights were between 2 and 6, right, then a 4 would be a 50%, and a 5 would be a 75%, and so on. Okay, so we're just going to transform it. We're going to rescale everything, both for the weights and for the years. So now we have all of our values are between 0 and 1. All right, and this is what it looks like. So this weight of 2950 got translated to a weight of 0.37, and this weight of 2130 got translated to this weight. We're looking at the end of the data set, so all of the years are 82, which is our latest year, so those are all going to be a 1. And now our cost curve has changed. So now look at this cost curve. So our scales are the same, right? There's a more clear point at the bottom, which is nice, and it's not quite as abrupt of a curve. So now let's try it again, right? We're just going to set our weights at minus 220 and minus 20, and we're going to tell it to go. And so now we started at 90, and we're taking steps all the way down, and it looks like we get to about 2.6. That's pretty good, right? We're within 2.6 on average of our miles per gallon. Here's what it looks like on the curve. This was our starting point. After one step, we were here, and we walked pretty quickly down to the bottom where we get our best possible mean absolute error. So that is how gradient descent works. And to close this demo, you can see now these are our new predictions. 28 when the actual miles per gallon was 27. At 29 for 27. This one was off by about 11. But in general, it looks like we did a lot better, right? And on average, we're only going to be off by 2. So that's pretty good. Now, this was one approach to machine learning. This was the gradient descent approach to machine learning. But in general, it's the same thing no matter what type of machine learning you're doing. You come up with a hypothesis. You tell the computer how to measure how good or bad that hypothesis is. You tell it how to update its hypothesis so it improves just a little bit, and then you just let it repeat. Just let it keep going. In that demo, we covered one of the big kind of gotchas that you'll see in machine learning, which is the deal of different scaled data. There's another one that I want to point out before we move on, because it's gonna show up in some of the other demos that we do. And that is something called overfitting. So a model that is overfit is a model that is too powerful for the data that it's working with. So on this particular slide, we've got 3 charts. We've got a model that is underfit, right? So this model is predicting a straight line when in fact our data has a pretty clear curve to it. We've got a model that's just right, where the predicted value follows the curve. But then we've got this overfit value. An overfitted model is, as you can see, it's making a lot of adjustments to itself to hit the exact data points that went into creating this squiggly line, right? And the problem with that is that if we were to then take this model and use it to try and predict new data points where they should, what the right y value should be given x, it's not going to be you're likely to be inaccurate because this line is so tailor fit to the data that trained the model that you're not going to generalize very well, right? Your new data is not going to perform well with the model. So what are some ideas in terms of ways that we can know if a model is overfitted or not? How would you go about figuring out whether your model has been overfit? You could look at deviation. Any other ideas? You're on the right track.
Inflection points.
Inflection points. Okay, yeah, you could look at how many squiggles does it make. That's a possibility.
You're just going to remove the outliers.
Remove outliers. That could do it. Any other ideas? Smoothness. Yeah, that's a possibility. A lot of what you guys are talking about are actually really good in terms of thinking about ways to overcome or remove overfittedness. But to test whether a model is overfitted, what we typically do is instead of using our full data set to train the model, we hold some of the data back and we leave it out of the training process. All right? And then what we can do is we can try that model with the data that we held out. We call it the test data set. Okay? We're going to try our model with that test data where we already know the right answers, but we're going to compare our predictions to our test data's right answers. And then what we can do is we can compare how well did the model perform with the trained data and how well did it perform with the test data. And if it performed a lot better with the trained data, then we know that it's been overfit, right? It's trying too hard to match exactly the trained data instead of being generalizable. Okay? And then what are some ideas for ways we can prevent overfitting? I think you guys have already kind of covered some of them, but let's hear some other ideas. Fed in more data? Yeah. You shouldn't be able to answer you helped me with this presentation.
Why is it back there not at y'all?
Any other ideas? There are two basic ideas. So collect more data, like Peter said. Collecting data is never a bad idea when it comes to machine learning. In some business cases, it's not feasible to collect more data, but if you can, do it. The more data, the better your model is going to be. The other possibility is to restrict the model. Some ideas were thrown out about the number of inflection points. A lot of that's going to come from like the amount of polynomials that you put in your model. And so if you restrict that, if you restrict how powerful your model can be, then it's less likely to overfit the data that it has in front of it. So those are the two general ways that we want to try to prevent overfitting.